to talk about parallelogram. We're going to talk about parallelogram law of vector addition. So we talked about triangle law of vector addition, and it's very similar to that as well, since it might look a little bit different by the figure, but it's actually the same thing. So first of all, let's write its statement to understand what it means. So it states that it states that if two vectors two vectors acting simultaneously at a point represent represent by at a point are represented. So let me move this. um, Two vectors acting simultaneously at a point are represented by two adjacent sides of a parallelogram of a parallelogram drawn from a point both in magnitude and direction. So keeping the magnitude and direction same, so both in magnitude and direction, then the diagonal then the diagonal of the parallelogram passing through the point passing through the point instead of the, let's write that. I think that would make that point, since we are referring to the point, this point, so it will be that point. So passing through that point represents the resultant of the two vectors of the two vectors both in magnitude and direction So obviously, if you're like me, you did not understand anything by this statement. So to understand this statement, it will be much more easier for us if we do some figures and try to understand this. So let's see what the parallelogram law of vector addition is actually for. So I'm gonna take two vectors, since if two vectors is represented right over here. So let's take two vectors. So let's make it in another page. I will take this as my first vector. The sizes doesn't matter, but I'm just trying to show. Let's make this white and let's make it thicker. And the second vector, let's make it at an angle. The vector can be at any angle as well, so let's actually make it much more slanted, because I want to make it much more slanted. And I will change its color to blue, and I will make it, so I think I did not change the color, so let me change the color to blue and make it much more thicker. So if we have two vectors, these are the two vectors, obviously. So let's go back to the definition or statement. So if two vectors acting simultaneously at a point, so both of this vector must act simultaneously at a point. So I'm just gonna copy this vector, and let's say they act simultaneously at a point, which means I must connect them by telltale method. So they're acting simultaneously at a point. It's why do we call it simultaneously at a point? Because if this was a point, so this point, the two vectors, so this blue one and the white one, are acting from that point. So they are acting simultaneously meaning at the same time, from this point. So now let's take a look at what is represented over here. So are represented by two adjacent sides of a parallelogram drawn from a point. So this is a part of the parallelogram. So these are two adjacent sides. Adjacent sides meaning they are just this side and this side are touching. So that's what it means to be adjacent side. So actually, let's complete the parallelogram to make it much more suitable, and also change this to make it some different color and something different. So let's make it dotted, um, obviously a lot more smaller, not an arrow obviously, and let's make it yellow. It's just my choice. So if this is a parallelogram, the any two adjacent side would be this one, or this one. So you can take these two yellow ones, or you can take this blue and yellow, or you can take white and yellow, but you can't take white and this yellow, the upper yellow. So adjacent meaning they are touching together. So let's go back. If two vectors acting simultaneously at a point, so they are acting simultaneously at a point, represented by two adjacent sides of a parallelogram drawn from a point. So represented by two adjacent sides of a parallelogram. So you must remember that it is the adjacent side, both in magnitude and direction. So as you can see, I did not rotate the vector, which means I did not change the direction, as well as I did not scale up or scale down the vectors, which means I did not change the magnitude. So if I did this, this would be changing the magnitude, and if I did this, this will be changing the direction. Since I didn't do anything, I'm keeping both the magnitude and direction same. So now, then the diagonal of the parallelogram passing through that point represents the resultant of the two vectors both in magnitude and direction. So we have these two vectors, and we want the resultant from this blue vector and this white vector. So we know the diagonal. So there are two diagonals in this case. One of the diagonal is this one, and another diagonal is this one. So according to the statement, the resultant is actually the diagonal that passes through that point meaning the point where these two vectors act simultaneously. So let's make this red, and let's make it a lot more thicker. And so this red arrow or vector is actually the resultant of the blue vector and the yellow vector. The vector can be anything, of course. So this is what the statement states. So this is the direction as well, this is the magnitude as well. So that was actually the visual representation of what I'm trying to show you. So now let's actually get some mathematical formulas which will make it much more easier to understand what we did. So it's pretty much the same as triangle law of vector addition. So if you remember or you watch that video of mine, it's pretty much the same. So now let's do some consideration. So let's consider two vectors, vector A and vector B. So let's write it much more clearly. Vector A and vector B. It's B with the arrow over it. It might look like this, but I'm trying to make like this. It's supposed to be an arrow, okay? So vector A and vector B, which are represented by the two sides OP and OS respectively of a parallelogram, OPQS. So this is the first part. We will also write much more, but this is the first part right now. So let's consider what the first part is writing. So consider two vectors A and B. So I'm gonna assume this one as vector A and this one as vector B, right? So now, and also let's go back, which are represented by two sides OP and OS respectively, which means and let's also see the parallelogram, which is OPQS. So which of these is OPQS? So this is OP, since A is represented by OP, and this is OS since B is represented by OS, which means the rest, this one will obviously be Q. So OPQS, that's the parallelogram we are talking about. So let's also write these A vector and V vector right over here. And another thing that I forgot to tell you, that how was I able to move them from tail to tail? It's because of parallel transformation. So as long as I don't change the direction or the magnitude, I can move this vector b or a at anywhere. So I just moved it like this. Yeah, so I moved it like this and the other vector like that. So I just moved it like this. So that's what I did. So now let's continue with the explanation to make it much more easier and clearer for us. So now um, let let theta be the angle be the angle between vector a and vector b. So what is the angle between vector a and vector b? In if you remember, in triangle law, we actually made this go forward to actually land it by tail. But luckily for us, this is already in tail by tail formation, which means this angle is theta. So pretty easy for us right now. So this is the pretty easy fact. Also, um, let's see. Let's continue. So now, according to the law of according to the law of according to the law of parallelogram addition, I don't know. Let's rephrase this. According to parallelogram law, it's wrong color. According to parallelogram law of vector addition um, the diagonal OQ the diagonal OQ represents the resultant of the two vectors i.e. meaning that means so I dot e dot, so which means, let's say resultant is vector r, which would mean it is vector a plus vector b. So this is what the resultant means. Obviously it's not adding the magnitude of them, it's considering the direction as well. So this is how you represent addition in vector addition. So now let's go back, which means this red vector is actually our, so let's make it much more clear. This red vector is our resultant, which we call r, vector r, and it is equal to the sum of vector a and vector b. So now, before we continue, let's try to understand why is the diagonal actually the resultant. So to understand this concept a lot more, I'll actually do this in another slide. So let's think of a ball, okay? Let's think of a ball, and if you think of a ball, it's pretty clear that it's at rest, since I have not made any arrows, so you can pretty much say that this might be on rest. So now I'm gonna draw some vectors and let's see what happens. Let's actually use the vectors over here. So I'm gonna copy this one, let's move it, let's keep it right over here, and let's take another one, this one, and let's put it right over there. So now my question for you is, if one man pulled the ball from this direction, suppose this is a rope and someone pulled it in this direction, whereas another man kept here pulls another rope in this direction, what would you assume that the ball would move like? So how would the ball actually move? If I were you, I would think that this is actually supposed to be like this, but so how would it move? So if you would ask me, I would think this would pull over here, this guy would pull over here, which means at the end of the day, the ball will move like this. So, and that's the resultant that we are talking about. So the ball will go in this direction like this until both the forces are cancelled out or balance goes to zero. So like this. I think this is pretty clear, and this is what I'm trying to say. So it will keep on pulling until both of these forces are balanced out or are equally balanced out. So it will probably be around here, and because in this case this vector blue one will actually go like, I'm just gonna make it with a pencil, like this, and this one will also go something like this, and they are both equal in magnitude and opposite in direction, so they cancel out. So that's how the ball is gonna move. So that's what this is illustrating and how we know that it works. So now, since we have this, let's think, what do we need to find of the resultant? If you ask me, I say you need to find the magnitude and the direction to know everything about the vector. So let's find them. So first of all, we're going to find the magnitude. So the magnitude of vector r. So that's the first thing we're going to find. So first of all, let's write OP is produced and dropped perpendicular at n from q. So if you watched my triangle law video, this is exactly the same derivation. There's nothing different about this, since if you find the resultant, you're gonna find the same resultant no matter what method you use. So if you use triangle law or parallelogram law, it's gonna give the same result. And understanding triangle law will be much more easier once you understand parallelogram law, since this is the parallelogram law, and if I just move it like this, isn't this the triangle law? Yep, it's the triangle law. That's why once you understand the parallelogram law, triangle law becomes much more easier, and vice versa. So let's see what we said. We said OP is produced and dropped perpendicular at n from Q. So we want to draw OP. So what is OP? This was OP, right? So let's make OP much more, what do you call it? Longer, I would say. So this is OP. So we are just extending it. We are not changing the magnitude of vector A. Rather, we are just showing how would the line go forward. If you understand what I'm saying. Not the best explanation, I think, but I hope you understand what I'm saying. So it's not that I'm expanding the vector in order to make this, but I'm just doing so, I don't know, but you get what I'm saying, right? So now, let's see. OP is produced. Yep, we produced OP and dropped perpendicular at n from Q. And I wrote drop and drop perpendicular at n from Q. So from Q, let's drop a perpendicular, and it might not exactly be 90 degrees, but just think of it as it is. So let's make this another color. Let's make this that one. No reason, just because I wanted to. So this is the perpendicular that is dropped, and it is dropped. So this is the perpendicular. This is the perpendicular, and this point is n, since you're dropping perpendicular at n from Q. So now let's take a look at some triangles, and before that, let's also see some facts. So this is a straight line, right? So OP produced is still a straight line, and this B and this OS and PQ are parallel. Since they are parallel, this angle right over here, QPN, is also going to be theta, right? And since opposite sides of what do you call this, parallelogram are equal, which means since the opposite sides of parallelogram are equal, it will mean that if this is B in magnitude, this will also be B in magnitude. So B in terms of BE, and also B in terms of B. Very confusing, I know, but this is also gonna be B in magnitude. Since I'm not writing the arrow, I'm trying to say this as B as in a length. And now let's go to this. So now let's take a look at some triangles and find out what we need. So from triangle PQN, so first of all we're going to take a look at triangle PQN. So before even seeing what PQN is, let's draw the triangle to make it much more easier. um, I think so. Let's go back here. Why do I need to think? I will just see it right over here. So PQN is a right angle triangle, so let's just make a right angle triangle, pretty easy. um, Right angle triangle. I think I gotta rotate it like this. So this is the right angle triangle, um, not to scale obviously. So now let's actually label it and see what we have. So let's go back and see how we're gonna label it. So this is PQN, okay. This is 90 degrees, and this is PQN, right? And let's go back. This is theta, this is B. So B theta. So actually let's make these another color to make it stand out, I would say. So now let's see what we need to find in triangle PQN. So first of all, let's use sine theta. So sine theta is P by H, so perpendicular by hypotenuse. The perpendicular is the length, which is not the hypotenuse, and which is not connected to the angle. So this will be QN. So QN divided by hypotenuse, which is the longest side, which is going to be B, and which is directly opposite to the 90 degrees. So before writing B, even though we need to write B later, sorry about that, that was a mistake. So what we are gonna do is gonna be QN by the longest side, which is PQ, right? And now we are gonna write QN by PQ is just basically B, so this will be B, right? So now let's do some cross multiplication, which means B is actually gonna be so let me rephrase that. QN is gonna be B sine theta. So let's call this equation 1. So now I'm actually gonna take the triangle once more, since we need the triangle again. So let's move the triangle somewhere above, like here, and continue with the triangle. So similarly, with its sine theta, now let's try cos theta. So cos theta is gonna be Pn. So let's, before doing that, it's gonna be B by H. So base is the not the longest side, which is connected to the angle, which will be Pn. So Pn divided by the hypotenuse, the longest side, which is PQ, which means Pn by B, since PQ is just B. So again, Pn turns out to be B cos theta, and this will be our equation number 2. I think this is pretty clear right now. Okay, so now let's look at another triangle. So from triangle O and Q. So what is triangle O and Q? It's actually just a triangle. Let's see, O and Q. So we are talking about this triangle. So let's make the triangle, obviously. Where is my right angle triangle? There's the right angle triangle. Let's make it like that, and rotate it. Yep. Let's go back and fill out what we need to fill out. So let's see the triangle. As you can see, O and Q. So let's write that. So O and Q, and obviously this is 90 degrees, since we are drawing a right angle triangle. And let's go back. OQ length is R. So OQ length is R. We are doing this one at a time to make it much more easier. So OQ is R in length. So this is R as in length, not in terms of a vector, but just taking the magnitude. So also let's make sure that this is a length by doing this. I'm making this video after quite a while. I took a break of sorts, even though you might not feel like it, because I have already pre-planned a lot of videos. So that's why I'm having a little bit difficulties to find what to say. Also, this P also here, let's write that P as well. So there is a line like this. I don't know where, it might be halfway, it might not be halfway, no idea. This is theta and this is P. We are mentioning this P because it will be necessary pretty quickly. So now let's use Pythagoras theorem, which says that a square equals to b square plus c square. Since we don't have ABC, we will have to just say that. So Pythagoras theorem is basically the hypotenuse square. Hypotenuse is OQ. So hypotenuse square times base squared plus perpendicular squared. So ON squared plus QN squared. Right now, we are quite not sure which is the base and which is the perpendicular, since no angle is mentioned. It can be both of them. So that's why Pythagoras theorem, it does not require the angle to be mentioned, since it's going to be the same either way. So now, we actually don't know the length of ON, since I don't know the length of ON, I don't know the length of ON, but I know the length of OP and PN. So I know the length of PN, and I also know the length of QN. So QN being this part, and OP also I know it, since this is actually A. I forgot to write that, so let's go back and let's take a look at it. This is vector A, which means OA is just going to be this length, right? So I might be jumping around, but I think this is pretty clear right now. So now let's just do some math. So OQ is R squared. So before doing that, let's actually just expand this. So ON is gonna be OP plus PN whole squared plus QN squared. So OQ squared is gonna be OP squared plus PN squared plus 2 OP dot PN dot meaning multiply plus QN squared. Now let's just add everything that we know. OQ is basically R squared. OP is basically A squared. PN, do we know PN? Of course we know PN, because we just found out it's B cos theta. So B cos theta squared is going to be B squared cos squared theta. So now again 2 OP PN, 2 OP times PN, so 2 times OP, which is A, and PN, which is B cos theta, plus QN. Q is QN. Do we know QN? We also know QN, which is B sine theta. So it's going to be B squared, since QN squared is B squared sine squared theta. Now you can take R squared and it will be A squared plus 2AB cos theta, and you can take B squared and you can take cos squared theta plus sine squared theta as common, and this will just be equal to 1. So this is a proof that you will find, and this is a pretty common thing that most students will know. This is 1, which means we get R squared equals to A squared plus 2ABB squared. So now let's go back and let's write R squared equals A squared plus B squared plus 2AB cos theta, which means the magnitude of the resultant, since R is just the magnitude of the resultant, which means the length, it will be length in terms of geometry, but in actuality it will be the magnitude. Since we are representing this by lengths, it will be length, but in actuality it's the magnitude. So length will be a special case of magnitude, if it makes sense. So it will be A squared plus B squared plus 2AB cos theta, and they are put into a square root, and this is actually the magnitude of the resultant of A and vector A and vector B. So let's call this equation number 3. So now let's conclude this, which is required expression for the magnitude of resultant magnitude of resultant vector. So we found the magnitude. Now let's find the direction. Now let's talk about the direction of vector r. So to talk about the direction of vector r, um, let's actually do some considering. So let phi be the angle made by vector r with vector a. So going back to our initial consideration or drawing, this one. So the angle between vector r and vector a is phi. So our obvious question is, why did we take the angle between vector a and vector r? Could we have taken it with vector b and vector r? Yes, we can. And another question that you might have is, why do we actually take it with vector a or vector b? So we actually take it with vector a or vector b with vector r. It's because we know the direction of vector a or vector b, which is pretty clear to us. We know where vector a or vector b is actually, since it is generally given, or you generally know those values. So you just need to find vector r in terms of where vector a and vector b is. So if I say, if you know that vector b is going this way, and I say vector r is 30 degrees upwards, you know that this angle is 30 degrees and it's that way. So if you know one vector, the direction of one vector, you can obviously find the direction of other vector if you know the angle between them in a 2D plane at least. So we are doing this 2D vectors, so this works. Instead of 2D, let's say in a plane this works. If you have a 3D vector, there will be much more, there will be 3 angles in play. So since we are doing this in 2D, we only need one angle to specify where vector r is. So now let's do the derivation. So from triangle ONQ, so we first of all must know what is triangle ONQ. So let's go back and see what is ONQ. So ONQ, it is the big triangle. So it's this one, right? So I'm just gonna take this one, since it is much easier to copy and paste rather than draw everything once more. So let's draw what is missing, the A, let's see, OAPN. So the missing parts are OAPN, this 90 degree, this theta, and obviously a new value that we found, which is phi over here. So now let's do some math. So let's do some geometry. So now let's use tan phi. So tan or tangent phi, it is p by b, which means perpendicular by base. So the perpendicular over here is which is not connected to the angle, so there will be qn. So it's qn by the base, which is this one, which is connected to the angle and not along the side. So this is on. But we don't know what on is. So we know that tan phi is qn also we know that, but we are not going to write it right now. But we know op, and we also know qn. So we know op plus qn. So now let's just put the values of them. So tan phi followed by qn is, let's go back and let's take a look at this. Qn is b sine theta. So qn is b sine theta divided by op is a, and qn is b cos theta. So qn is b cos theta. So this is what it is. So this is not actually the angle, it's actually the tan of the angle. tangent of the angle. But I find this formula much more appealing, but so that's why I'm keeping in the box. So the actual final thing that we need is this one. So to find the angle, you would have to use tan inverse b sine theta by a plus b cos theta. Let's call this equation number 5. And to remember this formula, I have a pretty neat trick, which is, since there is a tan, just think of sine by cos. So sine by cos is tan, and keep the angle, keep the vector or the symbol of vector that you used, that you are measuring the resultant with, over here at the bottom. Since we measured it with a is at the bottom, whereas the one you did not use will be with the sine and the cos. Pretty, or you can have your own ways to remember this, but that's just the way that I use. So now let's write the conclusion. So the conclusion is equation 4 and 5 gives the direction of resultant vector, Obviously, now we actually understand what we are talking about. So we know the magnitude as well as the direction. But obviously, something might be bugging you in the brain, which is, let's see this in action. And I also want to show you this in action. So to see this in action, let's take some special cases. So the general cases or all cases can just be done by this formula when we are dealing with two vectors. But let's see by using let's see the cases. So the first case that we're gonna see is when two vectors are acting in the same direction, which means the angle between them is, so before going to the angle between them, since you might not have a general idea what is the angle between them unless you watched my previous video. If you watched my previous video, which was on triangle law of vector addition, all of these will be very repetitive. How do you say it? I have no idea, but I hope you got what I'm trying to say. It's like repetitive. I think repetitive. That's the best I can do. So let's take these two vectors, right? So if you take these two vectors and if I line them up, what's the angle between them? Some might say 180 degrees, but if you remember, you must do it by head or tail method. But if you do it by tail method, it will be 0 degrees. That's why the angle is 0 degrees. Let's say this is vector A, this is vector B, so this is vector B. This angle between them is 0 degrees, so it's gonna be this is gonna be the resultant, just by general thought. So this is the resultant. And a question that you might have that is, which is how do you show this by parallelogram law of vector addition? Yeah, so imagine they are connected by tail. So obviously there will be another part of the parallelogram that will go like this, and so think of it like this. So think of this vector is just a little bit slanted. That would mean that there will be another vector like this, which is going like this, right? And to complete the parallelogram. So just think it's getting closer and closer, which means it will look like this, since that's the other edge, and it will go like this. I don't think I am explaining this very well, since pretty complicated to explain, but if you're think about it, just think about it, what I'm trying to say. So, and this will just be equal to that. So that's the resultant what we got. Hope that makes sense. Probably not, because even I thought, what the hell was I saying? Um, let's mind the language, right? So now let's name the resultant, which is r. Now we just need to find the magnitude and direction of r. Obviously, the direction of r is the same as a and b, so that's what we're going to find. So the angle between vector a and vector b will be, so phi will obviously be 0 degrees. So we are just seeing what the things are, and obviously the magnitude of r, vector r, is just the sum of a and b. So this right over here is actually referring to the magnitude. So it's 1 plus 2 will be 3 in this case. Always, it will always be 3 in this case. We're not talking about vectors, we're talking about the magnitude of the vectors. So now let's takes a look at how we got here. So first of all, let's use the magnitude. We know that the magnitude is vector r must be a squared plus b squared plus 2ab cos theta. So cos theta is obviously 0 degrees right now, and cos 0 degrees is cos 0 degrees. Let's use this one, cos 0 degrees. So the question will be, what is cos 0 degree? So cos 0 degree is 1, which will mean this will be a squared plus b squared plus 2ab, and this is just a plus b whole squared. I will put the arrows at the end, or I mean right now. So now the square root and the square will cancel each other out, which means that we will get r must be equal to a plus b. And let's call this, let's call this, this is the maximum value, and this is pretty much the same thing that we did in triangle law. So this is from equation 3. So now from equation 4 or 5, let's use 5. From equation, no, let's use equation number 4, why not? So equation 4 stated that tan phi is gonna be b sine theta a plus b cos theta, and the angle is 0 degrees. So let's write the 0 degrees, 0 degree, 0 degree. Sine 0 degree is 0, so it's 0 by a plus b, which means this is 0. This means, let's make it another color. So this means tan phi must be equal to 0, which means phi, so phi must be tan inverse 0. So let's write this in another page. I did this to write this on another page. So which means phi must be 0 degrees or 180 degrees. But in this case, it's always going to be 0 degrees, so we don't consider the 180 degree case. So to summarize this, the resultant will have the same direction as the given vectors. So that's the result that we came up with. So now let's look at the second case. The second case is when the vectors, when two vectors, since if you have more than two, it gets a lot more difficult. So vector law and parallelogram law do not work to all of them. You can use any two of them and do them, but if you have, let's suppose, 5 vectors, you can't use parallelogram law for all those 5 vectors at once. You can individually take 2 vectors to come out with the net resultant, which is going to be quite a long task if you ask me, but you can do it like that as well. Vector as acting perpendicular, so 90 degrees. So let's just make some vectors. Which one should I make 90 degrees? So let's make this as vector A. So A was obviously blue, if you remember. No, A was white, sorry. A was white and blue was vector B. Obviously, you can take any other vector. I can take P, Q, X, Y, anything, if I really wanted to. So they're acting perpendicular to each other. So let's complete the parallelogram, which will just how should I complete it? Let's take this. Let's copy this to here, and let's copy this to here. Let's change this color to maybe this one. I have no idea what I'm doing, if you ask me. And even if you're watching my video, sometimes you might feel like, what am I doing? Like, I literally have no plan. I'm just trying to teach because I love teaching, since learning is a gift. It's a very fun thing to do. If you are studying for fun, it's a fun thing to do because you can understand much more things, much more advanced concepts, and you can actually think about them. Um, so I spouted some things. Now let's go back. So this is vector B, this is vector A, and this is our resultant R. And if you think about the magnitude, the opposite sides of the parallelogram are equal, and in this case it is actually a rectangle since this is 90 degrees. So this will be B in terms of magnitude, which means R will be A plus B, A squared plus B squared in square root. So this will be what we will get for R. This is just by looking at the picture. Obviously we're going to find it by actually doing this as well. And if you remember, if this is phi, and sorry, this theta is 90 degrees, so phi, if you remember tan phi, so tan is P by H, so P by H, P by B, tan is P by B, P meaning perpendicular, this one, so it's going to be B by E. So these are the two results that you would expect to see, and you will see them shortly. So now let's go and use equation 3. So from equation 3 we have R must be equal to square root of A square plus B square plus 2AB cos theta. Theta in this case is 90 degrees, which means cos 90 degrees is 0, which means it will be square root A square plus B square plus 0. So R will actually be square root of A square plus B square. Now let's actually make this thing. I think it's called a radical. I don't know. Not gonna fact check that one. Normally I do, but I don't care right now. I just don't remember what this arrow thing is called. Not this line is called. Actually, there is an actual term in math for the line that you use in most of the cases. So now we got this one. So this is for 90-degree case, and also from equation 4 we have tan phi must be equal to B sine theta, so which is 90 degrees, divided by A plus B cos theta, which is 90 degrees. Sine 90 is just 1, and B cos 90 is 0, so it will be A. So we get what we actually thought. So phi must be equal to tan inverse B by A. So this is minus 1. It's not like this sign, it's minus 1. It's just that I'm writing that fast, so it gets like that. Okay, so now we did 2 cases. Now let's do another case. And I think this might be the last case, but not sure. Yep, this is the last case. So when 2 vectors are acting in opposite direction. So let's erase this. Acting in opposite direction, which means theta is 180 degrees. So if you watched my triangle law video, you might remember that this has 2 different cases for both magnitude and direction, and we are gonna see why. So first of all, let's think of it like this. So let's make vectors. Let's make this white, so this will be A, and another one, let's go here. This is also vector A actually, but I'm gonna make it double in size. And let's bring this back. Let's rotate this to make this in opposite direction, and let's make it blue, so this will be our vector B, and in this case let's make it smaller. So it's very difficult. So it's not difficult, and what I'm trying to say is, if you remember how I explained when I did find the resultant of that case, it's basically like this. Okay, so the resultant, think of a parallelogram that's at the limit of this, so it goes from here, here. So if you think about it, the triangle, the length of the diagonal will be this. So let's make the length of the diagonal. The length of the diagonal will be, let's rotate. Where is rotate? There is rotate. It will be like this. So why might be a very valid question, if you ask me. So think about it. So this side, the opposite side will be like this. So, and this side will be like this, and this side will be like this. So how can I explain it? Like I'm so confused. Like but I don't know. Like I just don't have explanation. Just take it as it is. If in my brain I can like very much visualize this, but in terms of explaining this, I have like no idea. So let's say I have no idea and move on. Sorry for that, I would say, but never mind. So let's just move on. So now, in both the cases, the angle is 180 degrees, right? So let's say this is vector A, this is vector A. Obviously you can take any other vector. I'm just taking vector A and B to make it my life much more easier, since I can use the same notations all the way through. So, and this is our resultant, and this is our resultant. So over here, our theta, the angle made with A and R, is going to be 180 degrees, and here theta is going to be 0 degrees, since they are in the same direction. Also here R is going to be, since B is bigger, it's going to be B minus A, since it's got to be a positive number. And here R is going to be A minus B. So as you can see, there are two cases, and it depends on which one is bigger or which one is smaller. You can phrase it in any way. So that's what we are going to see pretty quickly. So now let's look at this. So from equation 3, the resultant is square root of a square b square plus 2ab cos theta. So theta is 180 degrees in this case, and cos 180 degrees is actually minus 1. So this will be square root a square plus b square minus 2ab, since this is minus 1, which means this is actually the formula of two different cases. So what are the cases might obviously be the question. So let's actually this thing, my voice is starting to strain. I think these long videos are something that I really enjoy, but it really hurts my throat, but never mind. So this formula is actually applicable for two different cases. Number one is a minus b whole squared, and or you can also do b minus a whole squared. If you want to know why, just do the multiplication and check it out. Like, this is very basic knowledge, but just check it out. Or you can just think of it as taking a minus sign common and squaring it, which will give us a plus sign. You can think it of anyway, and in any way you want to think about it, the square root is going to cancel out with the square, so the resultant can be a minus b or b minus a. So it can be a minus b or b minus a. So to summarize this, so this is actually the minimum value. So this is always going to be the minimum value, but also this depends on, so it depends on greater value. So in this case, A is greater than B, and in this case, B is greater than A. So we did this so that we always have a positive result, since magnitude is always positive. So now, so from equation 4, from equation 4, tan phi is B sine theta. Sine theta is 180 degrees divided by A plus B cos 180 degrees. So B cos theta, but theta is 180 degrees. Sine 180 degrees is 0, so it's going to be 0 divided by A minus B, since cos 80 is minus 1. So this is just 0, right? So this is 0, which means phi is going to be tan inverse 0. And phi can either be 0 degrees or 180 degrees. Now you have to think about it. Does this work for 180 degrees? In the case where we did in the same direction, it obviously did not work. But in this case, both 180 degrees and 0 degrees seems viable when you think about it. So that's why phi will be 0 degrees or 180 degrees, depending on what the situation is. So this will be the value of phi. So to make it much more clear, depends on, this also depends on greater value. So now, final thing, a note of sorts, you might have a question, if alpha is the angle made by vector r with vector b, then so actually try to find the angle of this by using vector b and vector r. It's pretty similar to what you did with vector a, but you're just changing vector b with vector r. Wait, what? You're changing vector a with vector b. I think so. That's the right one. I'm not quite sure. Okay, now, so in this case, the formula will actually be tan alpha, and let's see. So it's tan, so it's going to be sine theta and cos theta over here. Since it is the angle made with b, so b will be over here, which means a will be over here. So that's the trick that I told you about in, I don't know, somewhere in the video. And so we use the trick to find this. And this, you can also derive this. This is pretty easy to derive. I'm not going to derive it, since it would basically be doing the same thing that I did. Same thing that I did. So this is pretty much it for today's video. So in the next video, we're actually going to talk about polygon law of vector addition, which is actually going to be a lot more easier, since it is a lot more shorter. So till then, bye bye.